Hello, everyone. My name is Harold Buitrago. I'm a geologist and currently PhD student at CICESE, which is the Center for Scientific Research and Higher Education of Ensenada in Mexico. Um, mm, I will talk about pitfalls of gradient-based workflows in geothermal studies. This this presentation derived from our participation of in the SEG Evolve program last year. The content I will talk about 5 points: an introduction. Then I will talk about some critical assumptions within the Fourier's law. Then I will talk about geothermal gradient in sedimentary basins. I will be some comparison between linear gradient assumption and the physical models. And finally, I will talk about some conclusions. Um, so what led me to this topic? I participate in the SEG Evolve program last year as part of the CCS team. We presented the the evaluation of a geothermal project in the image conference in 2025. The SEG Evolve program is a mentoring program where teams from different universities can have to evaluate oil and gas and recently geothermal projects. So for our case, the SEG staff provide us with information from the oil and gas industry. Um, we um, we used um, seismic lines, petrophysical logs, and also some temperature data in the shape of VHD database. Our study area was in Australia, is the Cooper Basin, which is the basin that you can see on the left. And for the exploration assessment, we were trained to follow this conventional workflow. I realized that it's really common follow this workflow, especially in the oil and gas industry. The first thing to do is that we need some database, in this case, borehole temperature. Based on that borehole temperatures and using a really simple relation, we can calculate the geothermal gradient for each well. In this case, we have to assume or measure the temperature on surface, and as we know the well depth, we can calculate that geothermal gradient. Then we construct this kind of geothermal gradient maps, and assuming that geothermal gradient is a constant and linear at depth, we can use the previous map to calculate temperature at different depths. As you can see, this is just the formulation for a linear function. Then, and it's an optional stage, we can calculate the heat amount of the heat stored in a certain volume within the basin. After the calculation of certain isotherm, in this case the isotherm 120 degrees Celsius, we can intersect or find the intersect of that isotherm with our target formation, and we can calculate some kind of volume of the formation that where temperature is greater than our temperature of interest. Then, based of that volume, some thermal properties and the physical properties of the rock, and using the temperature estimated, we can calculate the heat within that volume. However, and maybe it's not clear in a first view, that workflow that workflow is following the Fourier's law. So maybe I thought in that time and in that moment that the limitation of the workflow maybe can be found if we study the limitation of the Fourier's law. Uh, the first one is related with the heat. In the Fourier's law, the heat is considered that is a basal heat flow. It means that it is not considering internal heat sources. And in cases when we have internal sources, especially in sedimentary basins, we can maybe do some erroneous interpretation of the heat flow distribution in the surface. The second one is that the heat flow in the Fourier's law is considered to be vertical or nearly vertical. It means that if we have some kind of advection or another process that introduce horizontal heat flows, the Fourier's law can't accurately define where this anomaly comes from. And as the heat in the Fourier's law is only introduced on the base of the model, so we can associate the anomalies, the gradient anomalies, to the base of the model, and this can affect our interpretations, for example, in lithospheric studies. This and I will focus especially on this assumption in the rest of my presentation, is that thermal conductivity is constant. Maybe that simplification is reasonable in certain areas like crystalline massives or batholiths, where we have where the most rock are maybe igneous or metamorphic rocks. That's not warranted in sedimentary basins. Here we have some measurements of thermal conductivity along, thermal conductivity at depth in the Copper Basin, and we can observe that the thermal conductivity is varying in very short wavelengths, but also in another wavelengths, long wavelengths, right? This short variation could be related to lithological variations. We know that sedimentary basins are not homogeneous. We have here, we can have sandstone, limestone, claystones, different layers with different properties, with different mineralogy, and as a result, different conductivities. However, we can have more general processes that impact the thermal conductivity in sedimentary rocks. One of the most is compaction. This process is completely associated with the formation of sedimentary rocks. So compaction decreases or reduce, sorry, the porosity at depth. And we can observe that in petrophysical logs when we say the porosity log or density log. We can observe the result of compaction in sedimentary basins. Um, Sorry. So we have also variations in thermal conductivity. It's an assumption that in sedimentary basins is not warranted, is not satisfied. And just let me rewrite the Forest law question in this way. In this case, geothermal gradient can be seen as a function of heat flow and thermal conductivity. In case of, if we consider that thermal conductivity is homogeneous and that heat flow must remain equal in value, it means that that there is no heat sources within our basin. So we can use the geothermal gradient as an indirect measurement or as an indirect estimation of the variation of heat flow from the basement. One of the arguments that are commonly used to argument to enforce that the idea of constant geothermal gradient in sedimentary basins is that kind of plots where we plot depth and temperature formation, and then we fit a line, a straight line, and based on that line, we can so calculate temperature at different depths using gradient, using certain depth and the temperature on surface. Um, well, and so based on that assumptions, we can calculate some kind of isotherms in different sedimentary basins. In this case, I'm showing you some isotherms in calculated for the Janus Basin. However, you can observe that the isotherms are not sensitive to structural control. For example, the occurrence of faults or even the height of basement. And the variation in thermal conductivity within the sedimentary layer also is not considered in the or is not evident in the calculation of these isotherms. So just let me do this question is really this figure can be used to support the linear gradient assumptions. I think that we have enough information to evaluate or to test that hypothesis. In 2024, we calculated some geothermal gradients using BHT well depth for three different sedimentary basins in Colombia. And we observed this trend of the geothermal gradient, which is not a constant at depth. You can observe that a shallower part of the wells tends to show a higher geothermal gradient, and the geothermal gradient decreases systematically at depth, and maybe until reach some kind of regional geothermal gradient, right? Um, so we did the same for with the using the data from Copper Basin, and we saw the same distribution, a kind of decreasing of geothermal gradient at depth. In that opportunity, we defined two different zones in this plot. The first is the shallower zone, where we call this section as the non-stabilized geothermal gradient, and the deeper part of the graph was called as the stabilized geothermal gradient part. So maybe this kind of data has a lot of noise, a lot of errors, right? So we use this figure from Llanos et al. This is a temperature log, And of course, the slope of that curve, that with is the black curve is the log. The slope of that curve is the geothermal gradient, and you can observe that the slope decreasing consistently with depth. Of course, we have some variations when we change from layer to layer, but the general trend is an increasing with depth. So if we consider that this is occurring because compaction, we have to think about this relationship. The rock matrix and the porous volume relationship is increasing. It means that thermal conductivity increases at depth. Okay, maybe that four examples that I showed you previously are isolated cases. However, using this compilation of geothermal gradients of data around the world show the same trend. Continental sedimentary basins and oceanic sedimentary basins show the same trend and decreasing of geothermal gradient at depth. Well, so considering that the thermal conductivity increases at depth, we try to measure how important should be considered the that variation at depth versus or against a linear gradient assumption. To do that, we use a physical model based on the heat conduction equation. We discretize that equation using a finite difference scheme and following very conventional boundary conditions. After calculating temperature, we resample at different depths the same profile and calculate it using that temperature gradients. And using that gradients from this kind of synthetic wells, we interpolated a curve of geothermal gradients, which in a 3D case should be compared with a geothermal gradient map. Using that geothermal gradient curve and the function that I showed you previously, we can calculate temperature, and we calculate temperature again and compare the results of both temperature estimations. In the case of thermal conductivity, we use this equation to calculate effective conductivity as a function of porosity, conductivity of the rock matrix, and conductivity of the fluid. We consider, in this case, water. And the porosity was calculated following the Attis law using a compaction coefficient representative of sand compaction. The location of wells horizontally was random, but the length of the well was also considered as a random variable. It means with a average value and a standard deviation. This is because depending on the exploration objective, wells will target a specific horizon or preferred interval. That is what we see in oil and gas, in sedimentary basins studied by oil and gas industries. We don't have a homogeneous sampling of temperature. We don't have that kind of sampling, but an interval when the most of the wells are being drilling to achieve that specific depth. So I studied different scenarios, different cases. I only want to show you this one, which is very interesting in the case of Cooper Basin, because in this scenario we have a topography basement. We have a basement height And if you observe in the basement topography in Cooper Basin, this is occurring also in this basin. We have a lot of wells on the basement heights and really few wells in the depot centers of the basin. So this left part of this figure could be similar to the depot center in our basin, and on the right we can see like the basement height and how the well depth is being controlled by the basement topography. If we consider different values of thermal conductivity, in the case of in the left case, I consider 2.5 as the thermal conductivity, and on the right case, I consider just 2. And then considering also a constant heat flow, I calculated the geothermal gradient, and I obtained different values, of course. Um, then I calculated the depth for 3 different isotherms on the left and on the right. And the idea is the problem arises when I try to connect these isotherms at depth. I don't know if the isotherm in this case will going up slowly or it will going up rapidly. Maybe if a well in this location in the middle can help to define what is the behavior of the isotherm in this area. However, this is not the case, and this is not the case in Copper Basin. So the behavior of the isotherm is strongly controlled by the interpolation process. And it led us to really big uncertainties in thermal estimation, and not just as temperature estimation, but also as volume estimation. Well, I tried to simulate that case in my physical model. In this case, I assume this topography, this topography in the basement, and some wells in the profile. Then I obtained the solution, the physical solution of the temperature for this thermal conductivity distribution, and then using the VHD temperature, I calculated the geothermal gradient, and I obtained the estimation at depth of the temperature. Then to compare the physical model against the gradient-based model, I calculated the differences between these both models point to point or node to node, and this is the result. I have a really big thermal anomaly on the left side of my model, but in the physical model, in the real case, I don't have any thermal anomaly in that side. So the geothermal gradient base, when we have this kind of control, of structural control in the well depth, can let us to create some kind of artificial anomalies at depth. This white line is the zero error curve, and I use it as a way to calibrate the model, and also the points are the wells. Well, using the fact that the well depth is a random variable, I ran several simulations, Monte Carlo simulations, in 3 scenarios without noise in the data, considering 10% of noise and considering 15% of noise. And the idea here was trying to evaluate how sensitive is the estimation to density, well density. It means the number of wells per kilometer. And we observed that it's consistent that if we don't have enough wells in a certain area, this can lead us to have really big errors, even in the order of 80 degrees Celsius. This is even worse when we move away um, from the assumptions of the Fourier's law. In the case of Cooper Basin, we have some intrusions in this part, in the deeper part of the basin. We have some intrusions that works as internal sources, and when we have that kind of cases, the error that we can calculate in the estimation based on workflow, um, based on based on gradient based workflows, can increase to 100 degrees Celsius on either we can have more errors. It means that if we want to use the Fourier's law, we have to be careful of achieve or satisfy the assumptions, the internal assumptions of the Fourier's law. As conclusions, I have four big conclusions. The first one is that conventional gradient-based workflows are highly sensitive to their underlying assumptions. That depth-dependent thermal conductivity leads to systematic overestimation of deep temperature and in volume. And of course, overestimation of heat, heat amount of heat stored in a certain volume. Basement topography introduces sampling bias and artificial thermal anomalies, potentially misleading drilling decisions. And the last one, increasing well density, reduce error, but does not eliminate the introduced bias. As a spoiler alert, we are working trying to provide some kind of additional correction that we call compaction correction. And after applying that correction, we can significantly reduce the errors in the temperature estimations using the conventional workflow for temperature estimation at depth. That's all from my part. Thank you very much, and I'm open to hear your comments or your questions. Thank you.